So I will speak about a physical implementation of fluid of light that was just briefly introduced by Jacopo on Monday based on waveguide polaritons. So this work is a collaboration between different groups in France and Thorsten Ackermann, who is the next speaker, by the way, in Strathclyde. So in CREA, Jesus Zuniga Perez is growing the samples. Sophie Bouchoul, who is doing atom chips for Isabelle, is also doing the processing for our samples. The group of Guillaume Malpech and Dimitri Solnishkov are working on the theory, and my group on the spectroscopy. And in blue, you have the names, in blue you have the names of the younger PhD and postdocs involved in this activity. So I will first introduce fluids of light with waveguide polaritons, then explain how we design samples, how we operate the devices, and then enter really the fluid of light part of this talk about mode locking, cavity solitons, and how we are able to generate multiple solitons in this system. So start with waveguide polaritons. Polaritons are obtained when we strongly couple an exciton transition in a semiconductor to a photon mode. And because here we work on a waveguide geometry, it's different from the microcavity geometry presented by Sylvain on Tuesday, I think. So here we have a waveguide core based on gallium nitride, a cladding underneath. And so the photon line is almost linear in the first approximation. And due to the strong coupling between exciton and photons, we form new eigenstates called polaritons with a given Rabi splitting at 0-day tuning here. And when we operate this device as a laser, we create a large population of the exciton reservoir here. These excitons will relax and scatter down to the lower polariton branch. And if we can quantize the polariton on this branch with, for example, a Fabry-Perot cavity, then the occupation factor can go beyond 1, and we get stimulated relaxation and something analogous to a laser. So let me compare to other systems. In fact, compared to microcavity polaritons, here with the waveguide, we can propagate over longer distances, and we have a negative effective mass, but the drawback is that we don't have a ground state. The microcavity is introducing a ground state at k equals 0. Here, we go to much lower energies. Compared to gallium arsenide polaritons, the one presented by Sylvain on Tuesday, we have a much larger Rabi splitting, which is 66 milli-electron volts, so it's much larger than KBT at room temperature, and I will show results from 100K to room temperature in this system. The drawbacks are that we work with UV spectroscopy. For example, we don't have SLM, and so it's a bit more tricky. And final comparison with 2D materials, which are now very much investigated for polariton physics. In fact, here we can do clean room processing, and we have less degradation under operation. Okay, I will present the state of the art regarding 3 aspects. First of all, the strong coupling. The first strong coupling in a waveguide was obtained 12 years ago at Sheffield University, and the Rabi splitting was just 5 MeV, so it was only stable at 10K. And then, thanks to the nitride semiconductors, which have larger oscillator strengths and larger binding energy for the excitons, progresses have been made. So here at EPFL, strong coupling up to 100 Kelvin and with a large Rabi splitting here. And in our group 5 years ago, we went to room temperature with bulk gallium nitride waveguides. Regarding the nonlinearity, first of all, I want to emphasize the difference between chi-3 nonlinearities in most nonlinear crystals and nonlinear materials and the one we are exploiting. If we have a transparent crystal with a given excitation, then chi-3 is usually obtained under the whole transparency spectral range of the material. And this is the standard chi-3 nonlinearity. We have it in gallium nitride. It can be exploited in the visible, in the near infrared, and we can do many things with that. But if we have polaritons, then we have another nonlinearity, which is also chi-3, which expands just over a few times the Rabi splitting. And this is the one I will exploit in my demonstrations today. So the first demonstration of that, again at Sheffield University 10 years ago, was slow light and bright optical solitons in a gallium arsenide waveguide with very low threshold for this nonlinearity, only 1 picojoule per pulse. and going harder in excitation power, they obtained also supercontinuum of light based on that platform. So here, a pulse is launched at a grating. It will propagate over almost a millimeter in the sample and be decoupled to be collected here at the output grating. And during this propagation, below the threshold, in fact, the temporal profile of the pulse is spreading due to GVD, group velocity dispersion. And when the soliton forms, then the duration of the pulse is conserved. Okay, the same was then obtained 4 years ago at EPFL together with Sheffield with the nonlinear pulse modulation in a nitride waveguide. And the final part of this state-of-the-art is about lasers. So the first proposal of an amplifier based on that platform was 11 years ago by our colleagues from Institut Pascal. And then the first laser was obtained on a zinc oxide semiconductor with cracks as defining a Fabry-Perot cavity. So this was not well controlled. It was just defects during the fabrication process. Then in Lecce, there was a gallium arsenide polariton lasers in 2020. Our work I will present today on gallium nitride, and more recently another work by EPFL in a ring geometry, and I will work with Fabry-Perot cavities. So the aim of the activity over the past years was to combine the polariton laser and the nonlinear optics in a single device, and this is what I will show you today. So the laser, when we look at an SEM image, an electron microscope image of the sample, looks like that. It's a gallium nitride waveguide you see here, and distributed Bragg reflectors at the end of the waveguide. So if we look at the light propagating, it will propagate back and forth between the two mirrors, but it's not light, it's polaritons, as I said before. Okay, I will not spend too much time on fabrication here. Just saying that when we operate the laser, we pump the laser resonantly with the exciton transition here. We populate this exciton reservoir, and if we are below threshold, we look at the spectrum, which is outcoupled here or here. And this spectrum is composed of Fabry-Perot modes corresponding to the length of the cavity here. And then if we increase the pump power and we go to beyond threshold, then if we look at that mode here with a square, we will have a nonlinear increase of the intensity by 1 order of magnitude. We will have a decrease of the line width by a factor 2, which are the signatures of lasing here in a CW regime. So this was performed at just 70K, and the cavity is very short, 20 microns, so it's shorter than any semiconductor laser, in fact. How do we assess the strong coupling regime? In fact, usually if we want to assess the strong coupling regime, we will put a grating on top of the waveguide so that the wave vector will be encoded into angles. So this is what we did 5 years ago in order to see, as a function of the angle of the emission, how the dispersion is reproducing the theoretical one. But if we work on a laser, we don't want to put losses induced by a grating on top of the cavity, so we prefer relying on the free spectral range. Indeed, the free spectral range of a cavity is simply proportional to the first derivative of the dispersion. So here is the dispersion, here is the first derivative. It goes to 0 at positive detunings because we have a slow light regime at large wave vectors. And so if we put our experimental points on top of that dispersion, we see that we are clearly in the strong coupling regime, and we can evaluate the Rabi splitting in that kind of cavities. And it's maintained up to lasing. Coming back to the dispersion, we can select the energy where it's lasing and calculate the Hopfield factors for the lower polariton branch. And we calculate something like 40% excitonic and 60% photonic polaritonic modes, meaning that we have a 20 micron long cavity, but the wave that is propagating here is not photon-like, it's 40% matter-like and 60% photon-like, like in a polariton. Okay, something which is a bit out of the scope, but interesting for the polariton community. How can we distinguish between a polariton laser and a semiconductor standard edge-emitting laser? In fact, in an edge-emitting laser, we have gain in the pumped section, but if we have an unpumped section, we will have losses due to the absorption. And in semiconductors, gain and absorption are reciprocal processes. So if this unpumped length is more than half of the cavity, the losses will be detrimental to lasing. So you need more than half of the cavity to be pumped to get lasing. This is not the case with polaritons because we can decorrelate losses and gain. So if we put that on a curve, we can see that in fact the gain at threshold for polaritons can, let's start with the gain for threshold in a semiconductor laser. It diverges at half of the cavity. And for polaritons, it's not diverging at half of the cavity, it's going to 0. This is what we measured in our experiments. When we reduce the length of the pump down to half of the cavity, in fact, the energy we put in the sample to lase is constant. It's not increasing. And then it's increasing only when we go below that gain length. And it's the same if we rescale to the cavity length. It's the same for two lengths of cavity, 20 and 60 micron. So this is really a textbook comparison between the two lasers that was not possible in the microcavity geometry that we can provide here. And we had a discussion this morning about reabsorption, and we can clearly assess that reabsorption is in the upper part of the cavity is not taking place, which is specific. Okay, mode locking. So when we want to mode lock this laser, we can just turn a simple button, a simple knob, which is the temperature. Why is that? Because the gain broadens as we increase the temperature, and if we go from 70K to 150K, we switch to a single mode or almost single mode operation of the laser to a multi-mode operation. And here you see that at the laser threshold, already 10 modes are involved in lasing. And the increase in intensity is steeper when we go through threshold, but the threshold value is not so different between the two regimes. So this is related to stronger stimulated processes. If we follow each of the modes, we see a strong nonlinearity shifting the modes. It's working up to room temperature, so we looked at that more carefully. Again, based on the analysis of the free spectral range. So the free spectral range of the data points here below threshold are nicely overlapping with the theoretical curve. And if we go higher in excitation power, we see here the free spectral range of the curves that are here. And we see that, in fact, we have a blue shift, which is not rigid for all modes. In fact, some of them are strongly blue shifting, but not the other ones. And they align to a given free spectral range, which is corresponding to the same group velocity for all modes. So it means that now all modes can propagate with the same group velocity, and therefore the nonlinearity has been able to compensate for the group velocity dispersion. Let's compare with other systems like fibers, for example. Usually beta 2 is negative in fibers, but N2, the nonlinear refractive index, is positive. Here we are in the opposite condition, but again, it's a self-focusing condition. And we can see the linearization of the dispersion by the nonlinearity here. We can also look at the envelope of this spectrum, which is a second hyperbolic, which is a signature of solitons. And from that envelope, we can deduce the pulse duration in that system, which is 100 femtosecond. Okay, so we have spectral proofs of a mode-locked operation of the laser. What can be done about the temporal dynamics? In fact, the problem is that with a 60 micron long cavity, the repetition rate of this laser is 300 gigahertz. So time-resolved experiments are really tricky to be performed. So we have to rely more on simulations, and I will present simulations performed at Institut Pascal by our colleagues. And compared to many implementations of the Gauss-Split IFC equation that we have seen this week, here we have to perform simulation on both the photon field and the excitonic field because we cannot do the quasi-monochromatic approximation or the slow envelope approximation. But we include standard terms, stimulated scattering, white noise to start the nonlinearity, polariton-polariton interaction, which is a chi3 nonlinearity, the exciton here, and the cavity here. And based on that, we can see that simulation will produce the time spatial-temporal dynamics in the laser, meaning that at start, the pump is homogeneous in the 20 micron long excitation part, but then soliton will form, cavity solitons, and they will bounce back and forth within the cavity between the two mirrors that you see here, with a period that is 3 picoseconds as expected. And the soliton formation time is very short, 20 picoseconds only. Okay. When we compare to other semiconductor or fiber mod-lock lasers, we have to answer the question which kind of mechanism we are using. And in fact, the most well-known mechanisms are Kerr-Lenz, at least passive mod-locking mechanisms. So you have Kerr-Lenz is, for example, a titanium sapphire laser. And you can also have saturable absorbers. And this second scheme is quite similar to the one we have, because in a saturable absorber laser, you have gain in one part and saturable absorption in the other part. And you could think it's a bit similar to what we have here. So what we did is to change the length of the gain and the length of the unpumped part to see if the unpumped part was operating as a saturable absorber. And in fact, this is the result for a 20 micron gain length with a given threshold here of 1.8 nanojoules. And when we go to 50 micron length, so we reduce the unpumped part by a factor of 4, and we have almost the same threshold, the same line width of the pulse spectrally, so the same pulse width. So it means that we can safely conclude that we really work with a Polariton mod locking and not with a saturable absorber. And we can quantify all the parameters in that system. So I will not enter into the details, just saying that we have a very strong beta 2 for orders of magnitude larger than in fibers. We have a large nonlinear refractive index, and this leads to a very small energy per pulse per soliton of only 10 to the 4 polariton per soliton. So we are not able to go to 1 polariton per soliton, but at least this is one of the smallest value for soliton pulse energies in any system. And why is it mod locking? In fact, it's because we build our sample so that the cavity length is comparable to the dispersion length, 25 microns here, and the nonlinear length in the system of the same order of magnitude. So that's why we have mod locking in this system. Let me enter to the last part of this talk about multiple solitons and the dynamics that we explored more recently. So in such a cavity, when we pump the whole cavity, we have a single soliton, but then we try to play with shorter gain lengths and to move the gain part along the cavity like that. And what we observed is that when we have the spectrum as a function of the gain position here, we have different regimes. For example, here at the center, the spectrum is like that, with a second hyperbolic envelope, showing that we have one single soliton in the cavity. But if we move the pump spot to the edge here, then we have an envelope which is in 2 peaks, and which is a signature of 2 solitons in that system. And this is the same laser, we just move the part we are exciting with our laser, our pump laser. So what is changing between the two positions can be explored with numerical simulations, again by our colleagues from Institut Pascal. And when we pump at the center, the single soliton solution is quite stable. When we pump on the edge, in fact, many solitons can propagate. It's even harder to get stable solutions from simulation compared to the experiments. But we can have 2 solitons with different group velocities. You may barely see them here, showing that, in fact, the phase matching of the longitudinal modes is depending on one side on the mirror position, but on the other side on the polariton scattering and the reservoir-induced blue shift under the pump. Okay, we wanted to know if this 2 soliton observation is related to the fact that we accumulate over many realizations during one experiment, because we accumulate on the spectrometer CCD a few thousand of experiments per second. But we resolve this emission with a Streck camera in order to see individual pulses here. And in each of the pulses, we have the 2 solitons present, meaning that they really coexist in each realization. And finally, we we explored what's going on when we go to larger cavity lengths. And as you see on this map, where again we move the gain position along the cavity, you can see that we can have many, many situations with the first situation here at the center, a single soliton as usual. But then when we go away from that, we have two solitons with different detunings moving. At some point, we can even have three solitons here at this position present in the same cavity. And this may look complex and unstable, but in fact, when we change from one cavity to the next, we obtain exactly the same results in terms of patterns, meaning that this is not related to roughness of the waveguide or defects localizing the optical light, the optical field. It's really related to the nonlinearity taking place in that laser. So here we have more solitons because now the cavity length is much longer than or a few times longer than the self-focusing length, and it's again longer than the pump length. Okay, and here's the summary of my talk. So I've shown different operation regime for the laser Polariton, the waveguide Polariton laser. When we work in the mode lock regime, I've shown that the hierarchy between the main lengths involved in that system, the cavity length, the self-focusing nonlinearity, and the gain length is really determining in which regime we can operate this laser. We have a small footprint compared to fibers or optical atomic vapors. We can work within 100 microns. But the drawback is that we have a fast repetition rate, even so fast that time-resolved experiments are very difficult to perform. And we can operate at photon numbers which are very small compared to fibers or other systems like that. And let me show some prospects. So recently we have changed the geometry from Fabry-Perot cavity to gratings on photonic crystals in order to generate the same kind of bond state in the continuum that was shown by Jacopo with the results from Lecce on Monday. So we are presently reproducing such results in our platform. And we are also working towards electrical injection because we work at reasonable low temperature, 150 K. We can even push it to room temperature, and we hope to be able to release the constraint from optical pump and to go to electrical injection in that system. Thank you.